Hello. I will talk a little bit about who Univrses are and who I am, and also sort of what we do and how that relates to autonomous. So I'm very happy that Sune said that this is not only for hardware people, because we're not, we're software people, but we do the components that kind of enable autonomous hardware. So in brief, so Univrses is a team of top-tier computer vision, deep learning, and robotics scientists and engineers. As you can see, we have quite a high percentage of PhDs, which is really useful because in this area of computer vision, there's very little or no sort of development without research. So it's basically research and development for everything. So our PhDs are luckily very good at embedded development, and the, well, master graduates are also sort of versed in research. And then there's me. I'm the only non-techie person, so it's sort of less relevant for the area. So basically, coming back to autonomous, just kind of making an extremely simplified view of what we do is basically, if you start to the far right, you have some kind of input data first, and then you have sensor hardware, right? And what you want to get out from that sensor hardware is instructions to autonomous hardware, for example, which is why we're here, or some kind of API or interface to software, or interface to a user, right? And in the middle, the scene understanding stuff, that's where you kind of have to make sense of all the input that you get from the sensor hardware, which is basically ones and zeros and pixels and stuff. And that's where we come in. So we do sort of the sensing stuff, which implies sensor-specific filtering. If you want to have different data from different sensors and filter out others, you might have image processing, which is basically looking at the pictures and improving the quality of images. You have object classification, which is basically clustering pixels into objects that you can then classify and track. And then you have point cloud generation, which is basically what you kind of reconstruct or generate texture and sort of a 3D understanding of the input. And then you have sensor fusion, because normally in autonomous hardware, especially if you go for vehicles, you'd have a bunch of different sensors. You can have different sensors of the same type, like stereo cameras, or you can have radars and lidars and complementary sensor types. And these will always generate a bit different types of data, so you need to kind of fusion the inputs and normalize it so that you get sort of one coherent understanding of the world. You want to localize yourself and build a map so that you understand where you are in relation to different objects that you've identified, and you also want to know sort of how are you moving in the world around you. And then for autonomous vehicles, you also have the free space detection, which is basically understanding where can the vehicle go given the map around it. And since we're talking about this part, you also kind of have a decision-making layer that instructs the hardware and activates it based on the sort of intelligence that you, or the interpretation that you get from the sensor data. So again, this is very simplified, but let me know if I'm moving too fast or anything. So that's how we relate to autonomous. So here's an example how computer vision and deep learning enable robotic automation of sort of non-trivial tasks. And then an interesting example would be if you have an autonomous robot that's supposed to it has a task that can vary, and in the sense that you cannot program its movements in advance. It will have to adjust according to the situation. And some examples could be a robot that's supposed to grip stuff, and it has to adjust the grip, like the angle and how hard it grips, and to the weight, the volume, and the position of the object. It can be packaging, if you have, for example, in grocery stores or something, or any types of sort of packaging or transformation so packaging or post office or whatever, you have different types of objects that you want to pack in optimal ways. Then you also need to understand what types of objects are you dealing with and how can you optimize the packing for them. Same with sorting, navigating, monitoring, refilling, etc. So it's basically when the task at hand for the robot or the motion the robot is supposed to do differs depending on the situation. Then you need computer vision and deep learning for the overall understanding of the scene, i.e. what is happening here. The object identification, classification and tracking, basically what are the stuff that I'm supposed to be handling. Localization and mapping is basically where are they and where am I, and sort of how do I extend my robotic arm and pick it up and do whatever. And also sort of depending on the situation, interpreting your own tasks. So if you have a gripping robot, your task is to grip. But if you have a more complex task at hand, sort of refilling shelves at a store or something, you kind of have to interpret, first of all, is this shelf clear? Do I need to refill it? And what should I refill it with? So for all of that, you kind of have to have an intelligent interpretation of the scene that you're facing. So we do that a lot. Also, another example is in autonomous vehicles. This is what we do primarily. Our largest customer makes autonomous cars. And there we have a SthlmHW solution that enables, it stands for simultaneous localization and mapping, which basically enables a vehicle to understand its own position and build a local map of the environment without using external sensors like GPS and stuff. And as you see on this car, it's just an example, but you have a bunch of different sensors because you need to have what you call redundancy. You cannot be reliant on external data flow, because what if you get shut off from the GPS? The car, the truck, or whatever you're riding in has to be able to function on its own. That's also why you have a lot of different types of sensor, because in different environments and in different situations, the sensor data is complementary. So you mentioned in mines, for example, then you might want to use LiDAR because it's normally very dirty and can be quite difficult to see, also for humans. And in mines, for example, they're trying to, so I know Boliden is trying to automate a lot of their mines, so their ambition is not to be able to, or not to need to use lights down in the mines, because everything is autonomous. Then you can't be reliant on RGB cameras, because the RGB cameras look at lights. And basically, so the simultaneous localization and mapping is basically, if you look at the small icons down there, you have the sensor, you have a map, and you have your own position, right? So localization implies that you have a map, and you have your sensor, and you determine where you are. It's basically like when you walk around with your mobile phone and follow yourself on Google Maps. If you have mapping, then you have sort of, you know where you are, and then you interpret the environment in order to build a map. But if you don't know where you are, and you don't have a map, you need to kind of accumulate that yourself. And that's SthlmHW. So basically you use the sensor to make the map and your positioning in real time, which is pretty complex, but it's also really important to be able to rely on autonomous vehicles under all conditions. But basically, if you looked like on the first slide I had with a sort of very simplified ecosystem, I'll just sort of introduce briefly how that's very simplified. And I used the example of autonomous vehicles since that seems to be sort of a common theme of interest for us all. This is a picture I found. Sorry, this is a picture I found on the web, which is just this Comet Labs interpretation of the future of transportation stack. So as you can see, this is not really the traditional value chain that you're normally seeing in terms of vehicles and stuff. This is a huge ecosystem. So I've tried to break it down and just sort of talk through how the different layers interact, because this is an exciting future, and it's kind of growing on us right now because it's not really fixed yet. So basically, this is what it says in the far right of the pictures. You have basically a lot of different roles or a lot of different functions, which will have a lot of different types of actors in it, but this is all to enable autonomous for vehicles. So if you start very basically, we have the sensors at the very bottom, and this is basically the stuff that kind of drags in data from the environment, right? So the stuff at the far right on my first slide. So that can be, oh, now it's really hard to see what it says, but it says radar, LiDAR, vision camera, and then it says something else. I can't really see either. Oh, GPS, I think. And that's one type of actor. That's hardware normally. Then you have, what does it say? Intelligent manufacturing. And that's another different type of animal, right? And then on top of that, you will have the infrastructure and the connected cars. And then on top of that, you have the autonomous sort of system that kind of inputs to the car, actually the autonomy. And I guess you will talk a bit about the restraints on that or later. Yeah. And then you have, shit, this is really small. Then you have in-car intelligence and assistance. Then you have the safety and security, the services on top, like Uber and stuff. And then you have specialty vehicles. And so you see, there's so many different types of roles, and I think computer vision is primarily interesting here, or it's super important here. So it's basically for the mapping, simulation, and annotation, so understanding the reality in terms of the autonomy. And it's also the navigation assistant and stuff in terms of intelligence in the car and driver assistance. And then you have a lot of other sort of application areas which will be reliant on computer vision, but will maybe where computer vision specialists will be sort of sub-suppliers. So to summarize, maybe, simplify it a bit based on that very, very complex pictures. But basically, for autonomous and for computer vision's role in it, I think first of all, as you saw, it's an extremely complex ecosystem with a lot of different actors with a lot of different roles that we haven't seen yet. It's also really dynamic. And last but not least, it's like the practicable roles are largely to be defined, and by that I mean that we don't really know exactly right now, you know, which part of the ecosystems might viably be filled by the same type of actors. So you saw one sort of slicing of the cake, but how the cake will ultimately be sliced is sort of to be determined. So it's a very exciting environment, and yeah, I think I'm almost done as well. So if you have any questions on sort of the software part of it.